Welcome to our channel. In the world of quantum physics, incredible events unfold at mind-boggling speeds. Processes thought to happen instantaneously, like quantum entanglement, are now being directly measured in the tiniest fractions of a second, attosecond. It's like freezing a fleeting moment to uncover the subtle details hidden in plain sight. Together with a team of researchers from China, Professors Joachim Bergdorfer and his colleagues from the Institute of Theoretical Physics at Tehran are measuring these fleeting moments to understand how quantum entanglement actually happened. These scientists aren't focused on the existence of quantum entanglement, but are keen on uncovering how it begins. How exactly do two particles become quantum entangled? Understanding quantum entanglement. Using advanced computer simulations, they've managed to peek into processes that happen on attosecond timescales, a billionth of a second. Quantum entanglement is a strange and fascinating phenomenon where two particles become so interconnected that they share a single state. It's like having two magic coins that always land on the same side. Flip one, and the other mysteriously shows the same result, even if it's miles away. You could say that the particles have no individual properties, they only have common properties. From a mathematical point of view, they belong firmly together, even if they are in two completely different places, explains Professor Bergdorfer. This means that measuring one particle instantly affects the state of the other, no matter how far apart they are. In simple terms, entangled particles share a connection that lets them talk to each other instantly. Measure one particle, and you'll immediately know something about its partner. This strange behavior defies our everyday understanding of how the world works, making entanglement one of the most mind-boggling concepts in quantum physics. Measuring with lasers and electrons. As incomprehensible as the concept of quantum entanglement seems, it's no longer a matter of debate whether or not it's true, and that's not what this study is about. We, on the other hand, are interested in something else, in finding out how this entanglement develops in the first place, and which physical effects play a role in extremely short timescales, says Professor Eva Brzezzinova, one of the authors of the current publication. To explore this, the team looked at atoms struck by an extremely intense and high-frequency laser pulse. Imagine shining a super-powered flashlight on an atom. One electron gets so excited that it breaks free and flies away. If the laser is strong enough, a second electron inside the atom also gets a jolt, moving to a higher energy level and changing its orbit around the nucleus. So, after this intense blast of light, one electron is off on its own, and another is left behind but not quite the same as before. We can show that these two electrons are now quantum entangled, says Professor Bergdorfer. You can only analyze them together, and you can perform a measurement on one of the electrons and learn something about the other electron at the same time. Time gets fuzzy in attoseconds. Here's where things get really intriguing. The electron that flies away doesn't have a definite moment when it left the atom. This means that the birth time of the electron that flies away is not known in principle. You could say that the electron itself doesn't know when it left the atom. Prof. G. Bergdorfer notes. It's in what's called a quantum superposition, meaning it exists in multiple states at once. But there's more. The time when the electron departs is linked to the energy state of the electron that stays behind. If the remaining electron has higher energy, the departing electron likely left earlier. If it's in a lower energy state, the electron probably left later, on average around 232 attoseconds later. Measuring the unmeasurable. An attosecond is so brief that it's beyond the ability for most people to understand. Yet, these tiny differences aren't just theoretical. These differences can not only be calculated, but also measured in experiments, says Professor Bergdorfer. The team has devised a measurement protocol combining two different laser beams to capture this elusive timing. They're already collaborating with other researchers eager to test and observe these ultra-fast entanglements in the lab. Importance of quantum entanglement. Understanding how entanglement forms could have big implications for quantum technologies like cryptography and computing. Instead of just trying to maintain entanglement, Scientists can now study its very inception. This could lead to new ways of controlling quantum systems and enhancing the security of quantum communication. The journey doesn't stop here. Professor Bergdorf and his team are excited about the next steps. We are already in talks with research teams who want to prove such ultra-fast entanglements, he shared. By exploring in these ultra-short timescales, they're not just observing quantum effects, they're redefining how we understand the very fabric of reality. Quantum entanglement and the future. It's clear that in the quantum world, even the briefest moments hold a wealth of information. The electron doesn't just jump out of the atom. It is a wave that spills out of the atom, so to speak, and that takes a certain amount of time, explains Iva Brezinova. It is precisely during this phase that the entanglement occurs, the effect of which can then be precisely measured later by observing the two electrons, she concludes. So next time you blink, remember that in less than a trillionth of that time, entire quantum events are unfolding, revealing secrets that could change the future of technology and our understanding of the universe. The full study was published in the journal Physical Review Letters. Like what you read. Subscribe to our newsletter for engaging articles, exclusive content, and the latest updates. Check us out on EarthSnap, a free app brought to you by Eric Rolls and Earth.com.